Our next application of the law of large numbers is going to take you back, way back, to elementary calculus. And I'm going to articulate for you a simple little problem that you have assuredly seen before. But this problem is going to have a little kick in the tail. And this particular kick in the tail is going to come from statistical physics in the immediate aftermath of the Second World War. So, without further ado, here is a problem in integration. The setting? Suppose we are given a function f in one or more variables. For definiteness, think of it as a function of one variable, f of x. Right? And let's say this function is defined on the unit interval. To make sure things are well behaved, let's suppose the function is bounded in absolute value. In other words, the absolute value of f is no more than 1 everywhere. And our problem, our objective, is to evaluate the integral of that function. A picture, as always, is worth 1,000 words, so let me draw a generic function for you in one dimension. So let's think of a function f of x defined on the unit interval as I've sketched for you. Our objective is to evaluate j, the integral of that function over the unit interval. And of course, you remember from your basic calculus classes that this just stands for the area under the curve of the function. Now, we've seen in our basic calculus several examples of integration when the functions are well behaved. We know how to integrate trigonometric functions, exponential functions, logarithms, and so on. But of course, if one is given a generic function f, then one doesn't really have, in principle, an explicit closed-form answer for what the area under the curve is. And so then we are now in the domain of numerical integration. How does one proceed to go ahead and numerically estimate the area under the curve of a generic function? Now, what I'm going to give you, in principle, is a description of a function f. And what you will be able to do, in principle, is, given any value x for the argument, you will be able to look up or compute the value of the function f of x at that point. So this is the information given to us, the ability to construct or compute the value of the function at any desired point. Our objective is to determine an estimate for the area under the curve, the integral of that function. Naturally enough, for a numerical integration, we start by sampling the function at given points. And the simplest such idea might be to sample the function at 3 regular points, let's say at x equal to 0, at x equal to 1/2, and at x equal to 1. Now, we have 3 values for the function that we're going to read out through our lookup tables. So this is going to cost us 3 lookups of the table. We now know the values f of 0, f of 1/2, f of 1. How do we combine them? Well, we're simply going to add them up with suitable weighting factors. What are the right weighting factors? Well, it depends upon the particular approximation strategy that you use. You might, for example, have been exposed to something called the trapezoidal rule. The particular approximation I've shown you is called Simpson's rule. We won't derive it here, but it is occasioned by trying to fit a parabola around the function points, and then figuring out what the area of the parabola should be, and that'll give you an approximation for the area under the curve of the target function. Of course, this is a very crude approximation. We just looked at 3 values of the function and added them up suitably. Of course, Simpson's rule tells us how to go about this more generally by sampling the function more frequently at more and more points, and of course, the more you sample the function, the better the approximation. But we'll be satisfied with a very crude approximation. Let's just take these 3 values, add them up according to Simpson's rule, and Bob's your uncle. Here's your estimate for the function, admittedly crude. Now, with this as background, now let's see what happens when we have more than one variable for the function. So we want to look at how this problem scales with dimensionality. Of course, we could think of 2 dimensions, 3 dimensions, and so on. And we'll immediately jump to an abstract setting. Let us say we are given a function f of d variables. D, of course, stands for dimensionality. we're going to call the variables naturally x1, x2, x3 through x sub d. Let's say the function is suitably well behaved. In absolute value, it is bounded by 1 everywhere. And so what we're interested in is the integral of this function as each of the variables varies in the unit interval. And we're going to call this j. Our objective is to estimate j. Again, if f is well behaved, it's very regular, then we might hope to actually explicitly, iteratively evaluate this integral. But in general, for a generic function, that is hopeless, and we are back to numerical computation. Well, let's see what Simpson's rule says in a d-dimensional setting. Let's start with our lessons from one dimension. In one dimension, we just sample the variable at 3 points, 0, 1/2, and 1. What would you do if you have two variables, x1 and x2? Well, naturally, we'll want to sample the function with the first variable ranging across three values, 0, 1/2, and 1, and the second variable ranging across three values, 0, 1/2, and 1. And so we'll end up sampling the function on a 3 by 3 grid in the unit square. And that's where the function is defined. Excellent. How do we do it for 3 dimensions? Well, no problem. We're now going to look at x1 ranging over 3 values, x2 ranging over 3 values, x3 ranging over 3 values. In other words, we want to look at a function defined inside the unit cube. We're going to sample the values of the function at regularly spaced lattice points, 3 per dimension. And once you evaluate the function, we're just going to add up these values suitably weighted. Okay, and if you do all of this, you're going to get, oh, this is a horrible expression, isn't it? A messy-looking expression. But it is not too unintelligible, because if you look at what it is saying, what we are going to do is the following. Let each coordinate variable range over 3 values, 0, 1/2, and 1. For each selection of the coordinate variables, evaluate the value of the function at a lattice point. Now you've got a whole bunch of lattice points at which you've evaluated the function. Weight them properly, and Simpson's rule, or the trapezoidal rule, or whatever you want to use, will tell you what the proper weights should be. These weights will, of course, depend upon the lattice point. You saw, for example, in one dimension, the weights were 1/6 at 0, 4/6 at 1/2, and 1/6 at 1. Similarly, you're going to get different weights at each of the lattice points at which you're going to evaluate the function. Call these weights A, and identify the lattice point with a subscript x1, x2 through xt at which you've evaluated that function. Weight the function, scale by the weight, and add up over the lattice points. And Bob's your uncle. This is it. Now, of course, one doesn't want to do this by hand in more than 1 or 2 dimensions. But of course, it's easy enough to put into a computer today and very quickly churn out a sum, and out comes an answer, which is a crude approximation to the desired integral. Now, my objective here is to take a look at how the demands on our computation are scaling as the variables increase from 1, 2, 3, and so on. So I'd want to take a look at the dimensionality, D, of the problem, and how many computations I have to do in this simple approximation via Simpson's rule. Now, it's easy enough. Let's start with the simplest case, where we have one dimension. D is equal to 1. And as we saw, we need 3 lookups. So let's identify a computation with a lookup of the value of the function. Okay. Of course, there are also going to be things like addition, but I'm going to have a similar number of additions and so forth. So in one dimension, for the crudest approximation for the area under the curve, I'm going to need to evaluate the function at 3 points, 3 computations. What happens in 2 dimensions? Well, in 2 dimensions, I've got now a square and grid points, 3 per dimension. In other words, I have 3 times 3, or 9 places in the unit square where I have to evaluate the target function. In 3 dimensions, again, in each dimension I have to have 3 points, 3 times 3 times 3 gives me 27 lattice points inside the three-dimensional cube. And now we're beginning to see a pattern. How does it work in d dimensions? In each dimension, we want to evaluate the coordinates at 3 possibilities. So there are 3 times 3 times 3 and so forth. Number of possibilities, or 3 to the power d lattice points, and therefore we need 3 to the power d evaluations of the function in d dimensions. So far, so good. It seems very reasonable, very elementary, and of course, it is a very simple thing to program into a modern computer, if one so desired. Now, just to get a feeling for the scaling numerically, let's say what happens if we are dealing with, at a whim, say d is equal to 200 dimensions. If d is 200, then we're dealing with 3 to the power 200 lookups of the values of the function. Now, what is 3 to the power 200? If you translate it, it comes out to be a little bit more than 10 to the power 95. Now, pause for a moment to absorb this. This is a mind-bogglingly large number. To put this in context, some estimates of the number of atoms in the known universe put the number of these particles at about 10 to the power 70. Now, suppose you imagine that there are 10 to the power 70 atoms in the universe. Suppose somehow we could cajole each individual atom to do a function evaluation for you. And let's say each atom does 1 billion function evaluations for you every second. And each of 10 to the power 70 atoms in the universe do 1 billion evaluations for you. And you put them all to work at the same time. Even so, the number of evaluations you need, 10 to the power 95, even working at this rate, will require more time than the entire universe has existed up till this point. The moral of the story is that when the dimensionality grows, even the simplest computation to try to evaluate that integral, it seems so simple, so trite, so banal, but even the simplest computation is effectively impossible, even very crudely, very approximately. It is impossible not because I say so, or it is impossible not because we have not been clever enough in trying to find sums. It is impossible because the universe does not have enough resources to be able to compute this problem in a reasonable amount of time. Now, this is a little disquieting. You see, the numerical integration we are doing was so elementary, so simple. We're just adding up values of the function at a few places, apparently, but the few places blows up, even in a modest number of dimensions, say 200 dimensions. At this point, a student might well feel, oh, well, okay, so that's a bit weird, but what do I care? Well, problems like these arise naturally in statistical physics. Immediately after the Second World War, it became clear that physical understanding of the universe, especially an atomic understanding, was going to become the key enterprise in the middle to latter part of the 20th century. And there is perhaps no other domain of endeavor in science or mathematics where integrals in very large numbers of dimensions crop up so readily as in statistical physics. And so it became imperative for people to try to estimate integrals like these in large dimensions. Now, the fact that it appears to be physically impossible to find even approximations to the desired integral doesn't mean that the problem has gone away. We still have an integral left to evaluate. The question then is, what can one do, if anything? Now, this was a setting, as I pointed out, immediately after the Second World War. And a consortium of 3 individuals, Enrico Fermi, the noted physicist, John von Neumann, the mathematician at the Institute for Advanced Study in Princeton, and Stanislaw Ulam, yet another mathematician, got together and came up with a bewildering idea, a truly bewildering idea. The idea was to try to estimate this integral j via a chance-driven computation. Say that again. A chance-driven computation. What does it mean? I mean, isn't a computation something very precise? 2 plus 2 is always inevitably 4. Where is there chance in this game? Well, bear with me. This is the next part of our story.